So, we have about an hour and a half. I suggest that you all go potty now, and then we will be congregating on the party bus. Fun on wheels. Only way to travel, besides a monorail. You must not step outside of the ring, and you must always wear the safety mittens.
We don't have any safety mittens.
Probably left them in the trunk of my car. It's all right. It's all right. Here we go.
After years of having to do stupid things for Michael Scott.
31! 31!
There was the car.
I was ahead of the car. 31 is my new number.
31 is humanly impossible.
Go, Oscar. 31's my number.
That's impossible.
Beat it!
The employees in Scranton have finally gotten Michael to agree to an extended hourly wage. So this hourly wage is going to kick in whenever he makes them do things like beach games.
Yeah, come on! Come on!
Like, I just want to sell paper, dude. Just let me sell some paper. Because Michael is Michael, he doesn't just give everyone the same wage, and he doesn't do it based on merit. He writes down all the possible wages on pieces of paper, puts them into, I would guess, a magician's hat. I would guess that he has at least 3 or 4 magician's hats. And then everyone selects a piece of paper, and that's how they get their wages. So you can see here, we're going to let X be a variable that represents each person's hourly wage. And then you can see all the probabilities. It looks like, unfortunately, most of the employees picked $1, $2, or $3, and very few people got $4, $5, or $6. To start this video, I'd just like you to try as many problems as you can on this page. You should be able to get through most of them. If something doesn't make sense, you can skip it. And then once you've attempted all the problems on this page, hit play and we'll go through them together. So our first question is this a valid probability model? And the answer is yes. Is it fair for the employees? No, but it is a valid probability model. If you were to add up all these probabilities, they add up to 1. So this is the complete sample space. We don't have any probabilities that are smaller than 0 or greater than 1. So this is valid. And then for number 2, 587 is not a possible value of X because that wasn't one of the pieces of paper that Michael put into the hat, which makes X a discrete random variable. So X is our variable that's representing the hourly wage of each employee. It's called discrete because there's a countable number of outcomes. Here we have 6 outcomes, 1, 2, 3, 4, 5, 6. Easily countable. There's nothing in between the values, which is why no one can get paid 587 or 253 or anything like that. For the histogram, I used frequency on the left, although you could do probabilities as well. I just thought it was easier to label frequency. And you can see that this is very right skewed. Michael doesn't like losing money, so that makes sense. Okay, the probability that X is greater than or equal to 3. This would be the probability of selecting a person who makes $3 or more. So for a discrete random variable, it's sort of like, okay, I'm going to have all the employees line up. I'm going to randomly select one. X is that person's wage. The probability that X is greater than or equal to 3 is the probability that that person makes $3 or more. In this case, it's 39%. So I just added up the probabilities for $3, $4, $5, and $6. Very similar in number 5, this would be the probability that a randomly selected person makes $4 or more, because now it doesn't include 3. There's only an 18% chance that a randomly selected person makes $4 or more. Okay, the employees protested because it just wasn't fair. And once again, Michael being Michael decides to just change the values. He doesn't change the probabilities, he just changes it from 1 through 6 to 1, 5, 7, 10, 15, and 25. Does this fix the problem? No. Most people are still not making a lot, and there's still only one person making the most. But hey, he can say he did something. For the average of the X values, to find an average or a mean, we add up all the values and divide by the number of values. So 1 plus 5 plus 7 plus 10 plus 15 plus 25. Oh, not divide by 5, divide by 6. 1050. Oops. I can count. Does this value tell us the average hourly wage? If yes, explain. If no, why not? Well, most people are not making 1050, so I would say no, this doesn't really explain the correct wage. In fact, 82% of people, 8 plus 9 plus 6 divided by 28, 82% of people are making between $1 and $7. That's almost everyone making less than 1050. So this isn't really a good representation of X. So let's think about a way of calculating an average that would incorporate these probabilities. That way we're actually representing the average wage better. So one thing we could do is basically a weighted average. So we can take the first outcome, $1, and multiply it by its probability. Second outcome, multiplied by its probability. And just keep going. And if we do that, we get $5.89, which is a much better representation of the hourly wage for these employees. So here's what we just did in formula form. We took each x value, which I just called xi, and multiplied each value by its probability, or pi. This Greek letter here means summation, so we're adding them all together. This is a mean, and I'm using mu here because what we've just calculated is a parameter. This mean describes the population of all employees in Scranton, so it's a parameter, not a statistic. Remember that a statistic describes a sample, and this isn't a sample of the Scranton employees, this is everyone. This is actually on the formula sheet, so we're in the probability section of the formula sheet now, and you'll see discrete random variable x, and they give you the equation for the mean. And that's almost exactly how I wrote it, just it looks a little nicer. They also call it E here, which stands for expected value. Sometimes with probability, instead of saying the mean of x, we say the expected value of x. They mean the same thing. Now the idea of a weighted average isn't weird to most students, probably, because likely most of your classes are set up with weighted average, like 75% for tests, 25% for homework, or each marking period counts for 25% of your overall grade, something like that. Okay, so flip the page. Recall from chapter 1 that the standard deviation tells us the typical distance from the mean. It describes the variability, or the spread. The table on the right should look kind of familiar. We're going to calculate the standard deviation for x. We're going to do it by hand once, and then I will show you how to do it on the calculator. So pause the video and just do 9 and 10. Fill out the table, and then answer number 10. Okay, so for each value, I took the value minus the mean. Some of them were negative, most of them were positive. We square all those to make them all positive. The last column says weighted, so this is where we take each of these squared values and we multiply them by the probabilities. We can't just have a weighted average and not a weighted standard deviation. They both need to be weighted with some probabilities. When we add them all up here at the bottom, this is dollars squared, which is not very practical. This is called the variance. We need to get that into just dollars. So we square root it, and that gives us the standard deviation. Both variance and standard deviation describe variability or spread, but standard deviation is more practical because I don't know of any situation where you'll be talking about dollars squared. This doesn't really make sense. So our standard deviation is 5.01. Now doing that by hand is a pain. So if you want to do it on your calculator, here's how you do it on a TI. We've done one var stats before, but usually we just use one list. What we're going to do this time is one var stats and then put in two lists. So if you have an older calculator like mine, you're going to type L1, L2. L1 is your X values, so in this case our wages, and then L2 is where you put the probabilities. So you'll type in 8 divided by 28, enter, and it's going to change it to a decimal, but it's fine. If you have a newer calculator, you won't have to do this L1, L2 because your calculator will just show you a menu. For you, you're going to put the probabilities in the frequency list part of the menu. But either way, whether you have an old calculator or new calculator, running one var stats with those two lists is going to give you X bar, and look for sigma, that's the standard deviation. However, you should show at least one step of your work if this is a free response question. So here's an example of what I would expect to see on a test. Even though I know you're doing it on the calculator, I want to see that you know what your calculator is doing. So write out one step. This is also on the formula sheet under discrete random variable. It's over here, so you don't have to memorize it. Please don't memorize it. The interpretation for a standard deviation is the same as the last time we did standard deviations. So the wages for employees here typically vary by about $5.01 from the mean of $5.89. Okay, Michael decides he would rather assign wages so that employees could get any amount from $10 to $20, and all are equally likely. So this time we could have someone making $11.52, $15.95, or whatever. This is no longer a countable set of outcomes. I mean, like, you could count them all. $10.01, $10.02, $10.03, $10. But like, just don't do that. This isn't a discrete random variable anymore. This is what we call a uniform distribution. We could have anything from $10 to $20, and the probability of each value is exactly the same, so I just drew a straight line. The question is, what should we put here? So recall from earlier units, a density curve that's showing us all the possible outcomes. The area under the curve has to be 1. Because this length here is $10, I need to set this value so that the area under this curve, which I know is just a line, is 1. So since this is 10, I need to make this 1/10. That way the area under the curve is 1. So just a quick scenario. $15, right in the middle of 10 and 20. The probability of making $15 or less, I would take 10 to 15, so that's a distance of $5, and multiply by 1/10. That's 50%, which makes sense because 50% of people are going to be making less than 15 and 50% of people are going to be making more than 15. So this is kind of back to unit 2 where we're finding the area under the curve. Okay, I'm going to remove this stuff because the next problem says, what's the probability that an employee makes between 12 and 1250? So here's 12, here's 1250. What's the probability they make between those two values? So like we just did, the distance between 12 and 1250 is 50 cents. And I'm going to multiply that by the height here. And we get 0.05, which is 5%. There's a 5% chance that an employee makes between 12 and 1250. This uniform distribution is an example of a continuous random variable. So a continuous random variable is one where we don't have a countable number of outcomes. The uniform distribution is a specific type of the continuous random variable. The more common type is our old friend, the normal distribution. So let's shift gears. Instead of talking about wages, we're going to talk about the number of years that people have been working for Dunder Mifflin. The number of years can be modeled by a normal distribution. How convenient. The mean, mu, is 23 years. The standard deviation is 3.4 years. Suppose we choose an employee at random. Y is going to be the number of years employed. So here's a sketch. We have a normal distribution. Mu, the mean of the entire population of all Dunder Mifflin employees, is 23. And Y is going to be the number of years that they've been employed. So this is our example of a continuous random variable. There's not a countable number of outcomes because someone could be employed for 23.1 years or 25.26 years. It's not reasonably countable. Okay, so first of all, the standard deviation, same interpretation we've always had. The years of employment typically varies by about 3.4 years from the mean. Find the probability that Y is less than or equal to 25 and interpret this value. So this is the probability that a randomly selected person has been working at Dunder Mifflin for 25 years or less. Since we're dealing with a normal distribution, we are going to convert this into a z-score. And yes, we have done this before. So the first step here, I'm just going to take 25, subtract the mean, and divide by the standard deviation to get my z-score. So now I know that z has to be less than or equal to 0.588. 0.588 means that I am looking at a value just a little bit above the mean. Not a full standard deviation, but a little over half a standard deviation. So I'm expecting a number that is going to be greater than 50% because we are above the mean. Now you can use the table or the calculator. I'm going to use the calculator. So I'm doing norm CDF. I'm finding the area under the curve. Lower is going to be negative 1,000, just a small number. Upper, I'll go up to 0.588. And since I'm dealing with the z-score, I want the mean and standard deviation to be from the standard normal distribution. So that'd be 0 and 1. I get a probability of 0.7217. Now I forgot to interpret, so let's add that here. Okay, here's my interpretation. There is a 72.17% chance that a randomly selected person has worked for Dunder Mifflin for 25 years or less. Always double check that your answer makes sense. This is why the drawing is helpful. We were expecting something greater than 50%, so our answer does make sense. Okay, now that we've refreshed our memory on z-scores, why don't you try number 3 on your own? Pause the video and hit play when you're ready to go over it. All right, this time we have 2 z-scores to calculate, And our low z-score is negative 1.76, upper is 0.88, mean and standard deviation still 0 and 1, and once again we get a large number, and that makes sense because we're looking at almost 2 standard deviations below and almost 1 standard deviation above. So it makes sense. This is a lot of area to cover. There is a 77.14% chance that a randomly selected person who has worked for Dunder Mifflin between 17 and 26 years. It's a pretty wide range, so there's a good chance that that person has worked for that long. So that covers discrete random variables and continuous random variables. We're going to be looking at both of those in this unit. If that last example was confusing, I highly recommend that you go back and re-watch some of the videos about normal distributions, maybe even the extra practice video, just to refresh your memory. It's been a while, so that would be totally valid, but it'll help a lot as we go forward in this unit.